more efficient in some situations. It's called again, I'll label it either method 2 or call it the LCD method. And instead of converting the numerator and denominator of the whole fraction into individual fractions, what you're going to wind up doing here is you're going to look to cancel the fractions in the numerator and cancel the fractions in the denominator. And you do that by multiplying the top and bottom, the entire fraction. So here you're going to take this entire fraction and you're going to multiply it by the LCD of everything, every fraction involved in the entire problem. Okay, so your first step in this method is going to be to multiply the entire fraction by the LCD of each individual fractions. And whatever you get for the LCD of all the individual fractions. So as I look at this, I have a factor of x minus 5. That's one of my LCD factors. I have a factor of x plus 3. I have a factor of x plus 3, which is already included, and a factor of x minus 5. So these two factors right here are the LCDs, the least common denominator for every fraction involved in this whole problem. So I'm going to multiply the original expression, the original fraction, by this over itself. The reason I put it over itself is any number divided by itself has a value of 1, and multiplying any value by 1, it's an identity property, so it just equals that value itself. So we're not going to change the value here, just the form. All right, so our second step then is to distribute across the top of the original fraction. Okay, by original fraction, I mean the entire numerator up here. So there's my first thing. I'm going to take these LCD factors here, and I'm going to distribute them to the two fractions inside that original fraction. So what happens here is this x minus 5 cancels with this x minus 5, leaving my original x plus 1 times x plus 3. Then I distribute to the second fraction. The x plus 3's cancel. So I get plus 2 times the remaining LCD factor here, x minus 5. So this is the completion of step 2 for me, right here. So by distributing through, I've eliminated my fraction inside that fraction. Okay? I'm going to do the same thing across the bottom. Okay, so I'm going to distribute now across the bottom of this fraction. So now I'm just working in the denominator here, and I'm going to distribute this LCD to each of these terms. So in my denominator now, I'm left with x. The x plus 3's cancel, so I am simply multiplying by x minus 5 plus the next fraction's numerator x. Here my x minus 5's cancel when I distribute, so all I'm left with is the x plus 3. So this results from distributing the denominator across the bottom of that original fraction. And so now I've gotten rid of the complex property of this fraction. There's no longer a fraction within a fraction, it's just down to one single fraction. And so my final step here is going to be to simplify. Okay, so part of the simplifying is to go ahead and distribute this out or FOIL it. So when I do that, I'm going to work with just my numerator here. I get x squared plus 3x plus 1x gives me plus 4x plus 3. Distribute my 2. I get plus 2x and a minus 10. So once again, I get my expression here. Okay, and I can factor this, just like we did in the last example, into the two factors of negative 7, whose sum is positive 6, is plus 7 and minus 1. Okay, so when I look at this, I can simplify my numerator into this form, and then do the same thing in my denominator. So I'm going to distribute my x's and get x squared minus 5x plus x squared plus 3x. Again, combine straight down my columns. Factor, When I take out a common factor of 2x, leaving an x minus 1, I get my denominator. Okay, and so continuing with this process of simplifying, I can cancel my common factors, and I'm left with my final answer of x plus 7 over 2x, the same answer I got using the other method. Okay? So the advantage to this method is if you just have a few different factors and they're common to both the numerator and denominator, this way is it winds up saving time and often involves fewer calculations. Okay, however, the disadvantage is it's harder to identify the domain restrictions because all you see here is that x can't equal 1. What you don't see is in the original form, you have to go back and test for all the possible restrictions from the original form as well. And so if you do use this method, you have to go back into the original fraction, test for those also. So here we see x can't be 0, that's shown in the simplified form. X can't be a negative 3, that's not shown, so we include that. X can't be a 1, we include that. And x can't be a 5, we include that. So again, it's still possible to find those domain restrictions. It's just a little bit tougher when you're using this second method.